to the last part of the meeting of the lecture before the lunch. So it's going to be for something like half an hour. And in this lecture, my overall goal is kind of to give you a flavor of how Hmsc is working internally in order to fit models to data. So given that like we have limited time, very limited time, and we don't necessarily have, not necessarily all of us have a lot of well-developed skills. Do you see anything in the Zoom still, or has it just gone down? I mean, not me, but the screen. Okay. Somehow it doesn't display for me that like it's still. Okay, great. The main slide. Perfect. So basically, I would go over through the. I will start through going over through some fundamentals of Bayesian statistics. So kind of introduce you what is the difference between statistical model, likelihood of statistical model, prior and posterior. Then I will give a very brief summary of like what Markov chain Monte Carlo methods for sampling posterior distributions are and how they operate. Then I will focus more on the Gibbs sampling, which we use in Hmsc, and introduce the notions of conditional convergency and block updaters. I will proceed with showing how these fundamentals of Bayesian stats relate to Hmsc itself, particularly how they are reflected in the interface of Hmsc in order, for example, to change some of options of sampling for your particular model or customize a prior. And then after the lunch, definitely after lunch, I will have the code demonstration where we will take a look at the birds in Finland example already presented by Otso, and show how we can kind of customize some of the priors in that model and what effects they're going to have on the results. So first of all, let's start with the basics. So statistical model is just a formal formulation or a formal mathematical formulation which tries to encapsulate, kind of tries to capture some hopefully real life data generation process. Of course, like it doesn't capture it perfectly. It makes a lot of simplifications, and by making these simplifications, it also allows to formalize this notion of statistical model. Well, I have one minor question. So the screen behind me keeps jumping. Is it keeps jumping in the Zoom as well, or I'm not touching anything? So maybe if you're in the audience, it's even easier if you kind of look at the Zoom presentation. Well, because well, I have no idea what I can fix here with this system. So, well, like ultimately statistical model characterize what's the probability of different data being generated from given statistical model. So for each combination of data, it gives some probability that like particularly this data is going to be generated if we try to generate it from the model. And well, since it's probability distribution, it's designed in such a way that like the sum of these probabilities for each given data, they integrate to one. And there is a question in the chat about whether you have the presentation as well. And I guess Otso is now responsible for that part. So he will put my PDF, which I sent to him, to the Hmsc webpage on Helsinki.fi. So like, okay, what's next? So often statistical models can have a similar structure, so they have similar mathematical structure, but then this mathematical structure is enriching by inclusion of certain parameters. So while you can have the same structure, you can have very, very different models within that, which are parameterized by a set of variables or kind of set of parameters in such a way as it's displayed here on the slide. So here we denote this set of parameters by theta, and we say that like this probability of data is conditional on theta taken certain values. So then we come back to the likelihood, and likelihood is sort of like the definition of like is sort of defined as the reversed probability of statistical model, in the sense that like while statistical model describes the probability of data given parameters, likelihood describes the function of probability of data given the parameters, but it considers it as a function of the parameters. So in such way, when you kind of considering the statistical model and likelihood, you're often doing with the same mathematical object, but you're considering a different function with respect to different parameters. So in case of statistical model, it's with respect to the data. In case of likelihood, it's with respect to the parameters of the model. And we already saw like that Hmsc can be described in terms of statistical formulation. And here we have this summary. We will not go deeper into detail right now. Just that, just small recap that we have the so-called fixed effect part and the random effect part. And for both of them, we have extra hierarchical layers. For example, the fixed effect parts and the species niches are themselves modeled as regression with respect to traits, and potentially modulated by phylogenes. And the statistical model can be represented either in this simplified directed acyclic graph format, or maybe in a bit more developed statistical graph format, so which also has already shown earlier. And here I was just going to highlight what are the model parameters of hierarchical model of specific communities, and those are highlighted by red circles. So you can see that the duck consists of squares and circles, black squares and black circles, and in black squares we have the data, so something which is given to us as modelers or modelers, while in circles it's either the model parameters, which are double highlighted by red, or some quantities which are derived from that. And with these solid links and dashed links, we have either the stochastic dependency or non-stochastic dependency here. So in terms of when we say what is likelihood of Hmsc model, we just follow the standard notation that like likelihood is a function of data given parameters, and we consider this function as the function of parameters themselves. So these parameters, which are highlighted by red, they can be encapsulated into this vector theta, kind of meta vector, because it's a vector of various type of objects, not necessarily just scalars. And this is what we call the model parameters of Hmsc model. Okay, let's proceed further. And the next terms which appeared during lectures are the priors and posteriors. And these are the fundamental terms in Bayesian statistics. So the prior is a distribution of model parameters, so P0 of theta, which attempts to express the modeler's belief before he or she sees any data about the plausibility of these models for the given modeling task and for given application. We would not go right now into details how we construct priors which express these beliefs like in a proper way. So let's say that there are many ways, and those depends on the application and kind of the beliefs of the modeler. So one of the common approaches is to define so-called vague priors. So vague priors are kind of supposed to be covering well the regions which the modeler considers relatively plausible, but simultaneously not provide any kind of preference for particular areas within these regions, particular areas of model parameters within these regions. So then we come back to the like maybe the central object of Bayesian statistics. So this posterior distribution, and it expresses the plausibility of model parameters. So conceptually same as prior distribution, but given that we have observed the particular data and assuming that it was generated under a particular statistical model. So it can be formally expressed via the so-called Bayes rule as being proportional to the product of likelihood and prior distribution. And as you can see in the equation, it's also multiplied by the integral, so it's divided by the integral, which stands in the denominator. So this integral is the so-called normalizing constant of the posterior, and it comes in due to the fact that since we're talking about distributions, they have to sum up to 1 over the all potential values of parameters. Well, I say sum, but if we have continuous parameters, this sum is meant in generalized form, so it's actually an integral. Thus, in order to sum up to 1, once we integrate over all potential values of the parameter, like we have to put below this denominator, which is exactly the integral. So the task of model fitting in Bayesian paradigm actually means that we would like to find the posterior distribution or some approximation of it, which can be represented in some expressible manner, because kind of if we just say that if we just look at the formula, the central formula here, and say, okay, we have a posterior distribution which is proportional to the product of likelihood and prior distribution, it's not readily allow you to operate with this distribution, neither in computer nor in analytical form. Thus, you either need to properly calculate the integral below, or you need to find out some approximation how you characterize such posterior. So compared to the well-known maximum likelihood approach, which is a single point estimate, a model fitting in Bayesian paradigm typically means kind of obtaining much more information about the distribution, the target distribution, compared to just obtaining its single value. So here we have the first super toy example, and we have the prior, which is a standard normal prior, univariate standard normal prior, and then we have a likelihood, which is also a normal distribution. So then we can apply this Bayes rule to get the posterior in such model. So we multiply the prior by the likelihood, given that the observation in this toy example is that y equals 2, and then we can acquire the posterior. It is visualized in the figure here by the black color for the prior, like blue color for the likelihood, and then the red color for the posterior. So the next question becomes, how do we do it in practice? And for such simple univariate, like very, very toy example, this was possible because both like univariate distributions can be quite well characterized via some approximation on a grid. So if you kind of introduce a fine grid over the plausible values of prior, and which also covers the plausible values under the likelihood, then you can just multiply them, you can do the normalization in proper way, and you can obtain the posterior. Alternatively, you can derive this posterior analytically, because this prior and likelihood, they are nice and simple. However, like such analytical solution is available only for very few and typically very simple problems. Well, just like our toy example. So here, actually, there is a solution for this TOE example, which follows some formulas which some of you may know. So that for the product of two multivariate normal densities. But maybe we don't need to focus on this too much. Let's just kind of keep in mind that, like, for some of the models, it's possible analytically. For most of the models, it's not possible analytically. So when it's not possible analytically, one common approach is to characterize the posterior by obtaining some samples from such distribution. So once we have sample from this distribution, we can say that, well, we had the distribution, now we had samples from that. So like these samples represent the distribution because they were drawn from that distribution. And therefore, if we have enough of them, we can calculate certain quantities derived of the distribution using these samples only. Unfortunately, directly sampling using Monte Carlo techniques from such posterior distributions is generally equally complex as computing the denominator in this integral. Sorry, as computing the integral in the denominator. And instead, what is often used is so-called Markov chain Monte Carlo technique. So Markov chain Monte Carlo technique is a family of methods which introduce special statistical construct called chain, which sequentially acquires draws from the posterior distribution based only on the unnormalized part of the posterior. So based only on the product between likelihood and prior. So it's like it has really nice properties on the asymptotic behavior. So it's guaranteed that if the MCMC is designed in proper way, which is, well, fairly simple for many models. I mean, for most of statistical models, apart maybe of some very specific models. So if the MCMC is designed properly in infinity, once we run this chain for infinite, it converges to the true posterior. So it's, for example, unlike the optimization, it's not sensitive, at least in limit behavior, to the potential multimodalities of the target posterior function, so that it's guaranteed that, like, once we have done infinite iterations, we are in the true posterior. We have converged to true posterior. However, like in practice, these are like this infinite behavior doesn't necessarily stand, and it is challenged by two properties of MCMC, and one of them is the effect of starting position. So if you start somewhere with your parameter value somewhere far away from the true posterior, then it's inevitable that the first part of your posterior MCMC's sampling chain, you're going to spend in areas which have significantly less posterior probability compared to what they are according to the true posterior. And therefore, if you run your chain for finite number of iterations, because, well, neither of us have infinite time to wait once we can run these infinite chains. So once we run it for finite number of iterations, it can be that this initial phase, once we were kind of slowly going into the well, quite slowly, or not even slowly, but once we were going into the area of probable area for the model parameters, we have this, like, initial part kind of overweighted because, like, our chain is too short. So that issue is solved by removing the so-called transient phase of the chain. And the second very common issue is that because we're not doing Monte Carlo itself, we're not doing Markov chain Monte Carlo, there is an autocorrelation introduced by the statistical construct, which makes it that consecutive samples from MCMC are not independent. Therefore, we need, in order to acquire proper Monte Carlo samples of the posterior, we require to perform some thinning, so effectively reduce our whole chain of samples by some factor, which makes our samples from the chain that are separated by certain amount of iterations effectively independent. So then, like, MCMC has been a very widely used algorithm in Bayesian stats, and it's a constantly hot topic, so constant field of development both over past years and currently. So it has different sub methods, the kind of subtypes of approach how this MCMC can be designed. But in HMC we are using Gibbs sampling, and we're going to focus on that more. But if you are interested in MCMC in general, but maybe not on the very formula-based technique, but more kind of on the overall idea of how different MCMC techniques can work, there is a link in the slide to a very nice demonstration, which can kind of hint you what are kind of the pros and cons of different MCMC algorithms. It doesn't explain any of them, but well, you can kind of then maybe Google what these algorithms kind of about, what software implemented, and so on. So I guess at this moment it's good to make a small pause and reply some questions if they are. And has anyone been following the chat? Because I haven't. So do we have a lot of questions in the chat to read? No, not really. Okay, fine. I think we have 7 minutes more and we can go for the next chunk of my presentation. Okay, so what is Gibbs sampling? So the basic concept of Gibbs is that we don't want to solve a very complex problem of sampling from the posterior with kind of designing a complex MCMC, but like we would like to repeatedly solve much simpler problems of of adjusting a single parameter of our vector parameters at a time. So it's done by sampling only a single scale parameter, for which we have the so-called conditional posterior distribution, so which is represented here. I'm not sure if I can show anything here. Okay. So we have this conditional posterior, which is just a univariate distribution for the parameter theta I, conditional on the data, and conditional on all other parameters except theta I being fixed to particular values. So unlike the original posterior, the whole posterior, this is univariate conditional distribution. So it features only one-dimensional integration in its denominator, and thus many numerical techniques for approximate integration can be applied here. So sampling from such conditional distribution is called conditional update, a term which often appears in HMSC related terminology. And then the theory guarantees are that, like, if we cycle through these conditional updates through all parameters sequentially, it yields a valid MCMC sampling algorithm. There has been developed many software for generic Gibbs sampling, such as, for example, Bucks or JAX, and probably newer ones, which enable to use more efficient, not algorithm, but more efficient computation, so more fast computation perhaps. However, like these generic algorithms, they don't really consider that in some cases these conditional distributions can actually be derived analytically from within some known family, so that there is no need for numerical integration at all. And one important special case of such analytically possible derivation is the so-called conjugancy between the priors and likelihoods. So the case when the conditional posterior is belonging to the same family of distributions as the prior. So in some sense that like once we consider the prior as the function of the parameter theta I only, and we consider the likelihood also as a function of parameter theta I, their product belongs to the same family of distributions as the prior, as this conditional prior. So this property is widely used in Hmsc. So basically, I would say most of the statistical dependencies in between Hmsc parameters, they are designed in such way so that they support this conditional conjugancy, and this allows to almost avoid the need for numerical integration at all. So there is a sub version of Gibbs which is called block Gibbs, and that generalizes the Gibbs by enabling to sample the parameters jointly. So instead of like, for example, sampling theta I conditional on all other parameters except theta I and theta j conditional on all the parameters except theta j, we can sometimes derive or develop a sampler which samples theta I and theta j jointly conditional all other parameters except these two. And this in general reduces, like this for sure would reduce the MCMC autocorrelation. So it would mean that probably we would need either less number of samples or less thinning. And as the kind of cons of this approach is that like typically the joint distribution for these two parameters is generally more challenging to compute or acquire compared to each of them or each of them together, like each of them together. So I think it's 12 o'clock now, and are there any questions at this moment? So also, what do you think? Shall we pause at this moment and proceed later on?
Yeah, I think it's a very good time.
Okay, so let's make a lunch break for 1 hour and meet here at 1 p.m. Okay, also just announced that like the Zoom session will be closed for a moment,